René Descartes, when he invented analytic geometry, made a wonderful connection between geometry, that is, pictures, and equations. It was another 2 centuries before the concept of function was well understood, and in fact the connection of the function concept with the pictures of analytic geometry was at first a bit strained. For a straight line, there is no problem. If you want to describe the straight line, for example, through the points 1, 2 and -2, 3, you just write down the slope from those 2 points and equate it to y minus 2 over x minus 1, the slope between a point with coordinates x, y, and one of the given points, and you solve for y as a function of x. And that will describe the line completely in terms of that function. If you want to describe a circle centered at the point 2 minus 1, say, with radius 3, you can immediately write x minus 2 quantity squared plus y plus 1 quantity squared equals 9, but this does not define y as a function of x. What we can do, for example, is to allow 2 different functions, y equals minus 1 plus or minus the square root of 9 minus the quantity x minus 2 squared. Using the plus sign, we have one function, and the other one uses the minus sign. Now, there is a simple and elegant way to avoid this problem and get a representation of the entire circle with a single function. The technique is called a parametric representation of the curve. The idea is to recognize that pictorially, when you trace out a curve in the plane, or in R3 for that matter, you are taking an interval from the real line and bending it to make a curve. The analytic, that is, formula-based, description of this process is to recognize that for each real number t in the interval AB, you are assigning a point in the Cartesian plane with coordinates x of t, y of t. The variable t is called the parameter. As the parameter t moves along the interval from A to B, the point x of t, y of t traces out the curve. 2 things to notice. We can use any symbol for our parameter, t or r, or p or George. It doesn't matter. It is best not to use x or y for the parameter, since they are used to denote the coordinates of points in R2. The other thing to notice is that we are now dealing with a genuine function from the interval into R2, or if you prefer, a pair of real-valued functions, x of t and y of t, defined on the interval. For that straight line through the points 1, 2 and -2, 3, we know that we want to get the equation y equals minus 1/3 x plus 7/3. The confusing part is that we can use infinitely many different parameterizations to get this formula. The most obvious is to let x be our parameter. But we don't want to use the symbol x for the parameter, so we write x of t equals t, which means that x is the parameter, but we're giving it a different name. Y of t then has to be minus 1/3 t plus 7/3, and we let t range over the real numbers. Now it's clear that we have the correct connection between x and y, namely, y is minus 1/3 x plus 7/3. But we could make x of t equal 10t, for example, and still get the same straight line if we set x of t equal to 10t and y of t equal to minus 1/3 of 10t plus 7/3. X and y are still connected by the same straight line formula. The neat thing about this parametric idea is that we can generate pieces of curves very easily by restricting our parameter. For example, if we set x of t equal to t and y of t equal to minus 1/3 t plus 7/3, but we restrict t to the interval -2 to 3, then this parametric curve is just a straight line segment between the points -2, 3 and 3, 4/3. Notice that the parameterization actually determines a direction of motion along the curve. That is, as t increases, the point x of t, y of t moves along the curve in a specific direction. Now to the circle. Since our basic trig functions are intimately related to the circle, it is no surprise that they play a role in describing a circle by a parametric formula. Let's start with something very simple, a circle of radius 1 centered on the origin. So this circle can be described by the equation x squared plus y squared equals 1. When we have a curve or a function defined by an equation like this, rather than an explicit formula for y as a function of x, we say that the curve or the function is defined implicitly. Now this implicit equation looks very similar to the familiar identity cos squared theta plus sine squared theta equals 1. So we try the parameterization x of theta equals cos theta, y of theta equals sine theta, and let's let theta cover the range 0 to 2 pi. We can see from the picture that this works beautifully to describe the entire circle by a single function, capital F of theta, from the interval 0 to 2 pi into R2, given by the formula f of theta equals the pair cos theta sine theta, and theta ranges from 0 to 2 pi. But before you get too comfortable, realize that this is one of infinitely many different parameterizations for the unit circle. Here are two such. X of r could be sine of r, y of r could be cosine of r, and r ranges from 0 to 2 pi, with the associated picture. And here's another. X of u equals cosine of 2u, y of u equals sine of 2u, and now u will range from 0 to pi. Notice that we had to shorten the interval on which the parameter moved in the second example. What would have happened if we had missed this and written x of u equals cos 2u, y of u equals sine 2u, and u ranges from 0 to 2 pi? Well, you just trace the circle twice. And that is the beauty of parametric representations. First of all, we get a genuine function from the real line or an interval into R2 or R3. Secondly, it is very easy to describe pieces of curves or to trace out a curve several times, which, believe it or not, turns out to be extremely useful in, of all places, electrical engineering. Now let's have a go at our original circle, which was centered at 2 minus 1 with radius 3 and can be described by the implicit equation x minus 2 quantity squared plus y plus 1 quantity squared equals 9. Well, if I locked you in a room and told you not to come out until you found a representation, I think you would be opening the door in under an hour. But let me help. If you want to use our basic trig identity, cos squared plus sine squared equals 1, but with a 9 on the right-hand side, then just define x of t minus 2 to be 3 cos t, and y of t plus 1 to be 3 sine t, and let t range from 0 to 2 pi. Or in more conventional notation, x of t is 2 plus 3 cos t, y of t is minus 1 plus 3 sine t. As the picture shows, this parametric representation will generate our circle. All of the conic sections, parabolas, ellipses, and hyperbolas, have natural parametric representations. For the parabola, for example, y minus 2 equals 3x squared, which is already in a form that gives y as a function of x, just use x as the parameter. X of t equals t, y of t equals 2 plus 3t squared for t and r. For a parabola opening on the x-axis, for example, x minus 3 equals twice y minus 1 quantity squared, just use y as your parameter. So you set y of t equal to t, x of t equal to 3 plus twice t minus 1 quantity squared. Suppose you wanted to generate a piece of this parabola. Then just restrict t so as to generate exactly the piece you want. For example, the parameterization y of t equals t, x of t equals 3 plus twice t minus 1 quantity squared with t restricted to the closed interval 0, 2, generates the segment of this parabola between the points 5, 0 and 5, 2. If you use the restriction y of t equals t, x of t equals 3 plus twice t minus 1 quantity squared with t in the interval minus 2, 0, then you get the segment of this parabola between the points 21 minus 2 and 5, 0. For ellipses, let's take as an example the ellipse x minus 3 quantity squared over 4 plus y minus 1 quantity squared over 9 adds to 1. Again, we turn to our basic trig identity, sine squared u plus cos squared u equals 1. So you set x of u minus 3 over 2 equal to cos u, and y of u minus 1 over 3 equal to sine u, and restrict u to 0 to pi. This will give us the equation of the ellipse. In more conventional notation, x of u is 3 plus 2 cos u, y of u is 1 plus 3 sine u. Finally, let's deal with hyperbolas. Let's use the simple example x squared minus y squared equals 1. Here we need to recall the definition and basic identities for the hyperbolic functions. The cosine of u, hyperbolic cosine of u, is e to the u plus e to the minus u over 2. And the hyperbolic sine of u is the difference, e to the u minus e to the minus u over 2. So cos squared minus sin squared equals 1, which lines us up perfectly with the formula of the hyperbola. In the same spirit as when we dealt with circles then, we set x of u equal cos u, y of u equals sin u for u on the real line. But notice, this only gives the right half of the hyperbola because cos u is always positive. So far, I have focused on converting implicitly defined curves into parametric curves. Sometimes we need to go the other way. That is, we are given a parametric version of a curve and we want to get an implicit version. Some examples will suffice to show how we do this. For our first example, consider the parametric curve x of t equals 3e to the t, y of t equals 2e to the minus t, and let t cover the entire real line. For this simple situation, it is easiest to recognize that x of t over 3 is e to the t, and y of t over 2 is e to the minus t, which is just 1 over e to the t. Therefore, y of t over 2 is the reciprocal of x of t over 3, and when you clean up that equality, you conclude that xy equals 6, which gives you a hyperbola. But be careful. The definition of x of t as 3e to the t means that x can never be negative. So the parametric curve is only one piece of the curve given by our implicit formula. And this is a constant problem when converting parametric curves into an implicit formulation. You have to be very careful to check out whether the parametric formulation only traces out a piece of the implicit version of the curve. Now consider the parametrically defined curve x of t equals t squared minus 2, y of t equals 3t squared minus 6. Then again, by inspection, you can see that 3 times x plus 2 is equal to 3t squared, and that's equal to y plus 6. So you are dealing with the straight line y equals 3x. But again, you have to be careful, because x of t plus 2 equal to t squared is always non-negative. So you only have a piece of the line starting at the point minus 2 minus 6 corresponding to t equals 0 and moving to the right. In fact, if t is allowed to traverse the entire real line, since t squared is what appears in both x of t and y of t, we must trace out the line twice. After this warm-up, we can now tackle an example which is not solvable by inspection. Let's take x of t to be 2t plus 1 and y of t to be 6t minus t squared. In such cases, we can try to find a formula for the parameter t in terms of x and or y. In this particular case, we can use brute force by solving each of the equations for t. X of t is equal to 2t plus 1, which you can solve to get t equals x minus 1 over 2. Y of t is a quadratic in t. Y equals 6t minus t squared. In other words, t solves the quadratic equation t squared minus 6t plus y equals 0. And that, by the quadratic formula, has the solutions t equals 6 plus or minus 36 minus 4y square root over 2. So we can equate these two expressions to get an implicit formula for the curve. T on the one hand is equal to x minus 1 over 2, and on the other hand is equal to 3 plus or minus the square root of 9 minus y. We can clean this up and take the square to get a much simpler expression. X minus 7 is plus or minus 2 times the square root of 9 minus y, and squaring that says that x minus 7 quantity squared is 4 times 9 minus y, which is just the equation for a parabola opening downward. As a last example, consider the parametric curve x of t equals sine t, y of t equals 2 plus cos t, and let's assume that t is restricted to the interval 0 pi over 2. On that given interval, the function sine t is 1 to 1, and so has an inverse. Then we can solve for t in terms of x. T is the arcsine of x. Now you can solve for y as a function of x, because y is equal to t plus 2 cos t, and that's equal to arcsine x plus twice the cos of arcsine x. Now, in fact, you can simplify this implicit formulation by drawing a picture of the angle t equals arcsine x. And from that picture, you can see that twice the cosine of arcsine x is just twice the square root of 1 minus x squared. So we actually get an explicit formula, y equals arcsine x plus twice the square root of 1 minus x squared. To finish this lecture, I want to point out that implicitly defined curves occur quite naturally when studying surfaces in 3 dimensions. Suppose, for example, that the barometric air pressure at ground level over a county is given by a function of position. If you put down a coordinate system, then at the point with coordinates x, y, the pressure would be some function of position, p of x, y. As a ridiculously simple example, the pressure might be given by the formula p of x, y is x squared plus y squared. Then meteorologists are interested in the isobars, the curves along which the pressure is a constant value. For example, the curve along which our given pressure, p of xy equals x squared plus y squared, is constantly 4, would be defined by the implicit formula x squared plus y squared equals 4, which is obviously a circle centered on the origin of radius 2. In general, given any surface, such curves are called level curves of the surface. For the surface p of xy equals x squared plus y squared, the level curves are all circles, since p of xy equals k defines the curve x squared plus y squared equals k. Of course, the more complicated the surface, the more complicated the level curves.